This is our second lecture on double integrals. And in our first lecture, we motivated the idea. We talked about the double integral being the limit of a Riemann sum. And we, I guess our motivation involved volume. And then we looked at some iterated integrals over rectangular regions. So you've got a surface. That surface lies above, or part of that surface lies above a rectangle. How do you calculate the volume? And the volume is given by a double integral. Today we're going to look at iterated integrals over other regions, non-rectangular regions, and also look at the area of a region. Okay, so in this picture, we've got some surface in light green, and you can see that if we want to calculate the volume above, of the solid below the surface and above the x-axis, well, the so-called base of this solid is in a rectangle in this particular picture. Now, how do we calculate the volume of such a solid? Well, we can do it using the limit of Riemann sums. And now, we set up our Riemann sums involving these yellow rectangular prisms. But it's only going to work for regions R that can be approximated well by a partition of rectangles. So you want to cover the base with a partition of rectangles. Now the exact details of what regions you can and can't do that with is probably beyond the scope of this course. So just trust in the fact that the type of regions we'll look at, you can approximate them well by just a partition of rectangles. So what kind of regions, two-dimensional regions, does this include? Well, circles, ellipses, polygons, and other kinds of even more general regions. So the two-dimensional region, think of it as a base. In this setting, you can set up your Riemann sums, and if the limit of this Riemann sum exists, then that number, that real number, is called the double integral of f over the region R, and it's denoted by this notation here. Okay, so just to remind everyone, you sort of slice up your base into, forming little rectangles. You choose a sample point in each rectangle. You get the height from evaluating f at the sample point. That gives you the volume of a rectangular prism. Add all those prisms together and take the limit. All right, so yesterday we looked at these iterated integrals, Fubini's theorem. A double integral under certain conditions is just an iterated integral. What is it like for these non-rectangular regions? Well, it's very similar. So I'm going to look at two cases here. Suppose I've got this, on the left-hand side, this green solid, and I want to calculate the volume. Now, if you look at the base of that solid, it's bounded by two constant lines, parallel lines, constant parallel lines, and two non-constant lines. Well, using the same techniques that we used yesterday, okay, for each fixed x, we can calculate the area of this cross-section. So for each fixed x, that's just a number, that's just a number, that's just a function of y. And then to calculate the volume, I'm going to integrate from x equals a to x equals b. So I'm integrating that cross-sectional area from x equals a to x equals b to form a double integral. Sorry, that should be a G2. Okay, it's a little bit messy, but I hope you can see it. Now notice that the constants a and b are on the outside integral. You want this to be some number. So if you sort of switch those over, it wouldn't give you a number, it would give you something involving x. Okay, there's another way we can do it. Instead of sort of making our cross sections parallel to the YZ plane, I can make the cuts parallel to the XZ plane. So over here, basically, once we have, we can use slicing techniques to say, okay, the volume's this, and the cross-sectional area is just going to be this inside integral. Okay, so there's some motivations for these more general regions, these more general bases, and the volume associated with solids. Is there a Fubini's theorem for these more general regions? Well, yes, there is. So instead of a rectangle, suppose I've got a region R that's bounded by two sort of parallel constant lines and two possibly non-constant curves. If these two functions are continuous, then the double integral of f over this possibly non-rectangular region R is just this iterated integral. Okay? And similarly, if you define your R in this way, so y is between two parallel constant lines and x is between two possibly non-constant curves, with these curves, the functions continuous, then again, we can think of this double integral as just this iterated integral. So let's do one and actually find out what, how we would actually calculate something like this. So in the last lecture, R was always a rectangle. Here it's just a two-dimensional region that's can be described in either of, at least one of these ways. So here's a two-dimensional region. Think of it as a base, I guess. And let's just pick a function of two variables, say x plus y. What do we mean by the double integral of f over this particular R? Well, Fubini's theorem says that Okay, x is bounded between two constants, y is bounded in this case between two functions. Well, the double integral is just the following iterated integral. So numbers go on the outside, the functions go on the inside. Y is between these two functions of x, so I put the dy in there, and then I put the dx in, because x is between these 0 and 1. Now, to evaluate these integrals, it's the same as any iterated integral. You do the inside integral first, and then you move your way to the outside integral. So if I'm going to integrate the inside integral, I imagine the x's are constants and integrate with respect to y. So I'm going to get xy plus a half y squared. Okay, that's y equals x squared down there. So let's put in, replace y with x and replace y with x squared and do the normal calculation that we would. So if I put in y equals x, I'm going to get x squared plus a half x squared. So I'm going to get 3 on 2 x squared. And if I put in y equals x squared, I'm going to get x cubed plus a half x to the 4th. So now I've just got a single integral, and I know how to evaluate that. Okay, so I can integrate this. Okay, I'm going to get something like the following according to my calculations. What's that going to be? Okay, so if I just plug those in, according to my calcs, I get 3 on 20. Okay, so it's not very much different. The actual calculations are not different from what we did yesterday. You do the inside integral first, then move your way on to the outside integral. But here, we were lucky. We were given the mathematical description of our region. You don't always have that. So what a lot of students find challenging is to actually describe the region, describe the two-dimensional base, mathematically describe it. Okay, here we were given it, so we knew, okay, well, we just put these in here and these in here. So this looks easy, and it is, but the next problem is not so easy. Mathematically describe the following region R in 2 ways. Okay, it's a filled triangle. So what I want to do here is describe it either using, using this form and using this form. Okay, so 2 different ways. So the question is, how do you describe it? Well, you may remember the descriptions in your own way and the process in your own way. I'm going to show you one way of doing it. Okay? So let me show you. Let's say I draw a horizontal line. Now, going from left to right. If I look at that horizontal line, it enters the region R here, and it leaves the region here. So I can use that to form 2 bounding functions on my region. So our horizontal line enters R at the line y equals x, and leaves are at x equals 1. So this means that x has got to be greater than y, it enters there, and it leaves at 1. And so x has got to be less than or equal to 1. Okay, so that's sort of given us half a description. Now, let's look again at this horizontal line. Where do I move the line up and down to cover the entire triangle? Well, if I move the line between 0 and 1, I can cover that line will sweep out the entire triangle, right? So if I wanted to draw something else in here, I guess I'd draw a little interval here. So along that interval, the horizontal line is always cutting, and I guess it's filling up the rectangle. So here we would say y is between 0 and 1. So what's our description then? Well, this is our mathematical description. We can use that now if you wanted to, say, calculate some sort of double integral of some function defined on that rectangle. The question does ask us to do this two ways, though. So can anyone suggest how we might re-describe this in a different way? An equivalent way, but just a different way. Yeah, draw a vertical line. Okay, so if I just sort of try to repeat this diagram down here. Now, instead of drawing a horizontal line, what I'm going to do is draw a vertical line. Where does that vertical line enter our region and where does it leave? Well, it enters here, that's the line y equals 0, and leaves here. So what's y got to be between? Well, it's got to be between 0 and x. Now, let's do the same thing, but move this vertical line horizontally. What would my interval of interest be to sweep out the entire? It's going to be 0 to 1. Okay, so if I move this line anywhere between 0 and 1, well, if I move it between 0 and 1, I sweep out the whole triangle. So this is my second but equivalent description. That's one way of it's just a method that some people use to help them describe regions mathematically. Sometimes the regions can get very, very difficult. This is one way. If you have another way, as long as it works, I've got no objections to using it. Okay, well, the next question wants us to use the information that we've just calculated here to solve the following problem. Apply your ideas from the previous example to calculate this double integral. And by R, they mean this region here. Well, I know by Fubini's theorem that all I'm really doing in this question here is integrating this function over the rectangle. I've described it either this way or this way, down here. There you are. So it's up to me to choose, do I want to do the iterated integrals with this setup or this setup? Sometimes one's easier than the other. Sometimes it's not. Sometimes it doesn't really matter. So let's just, remember this will correspond to the volume of the following solid. Because we've been at the moment we've been interpreting double integrals as volume. So by Fubini's theorem, our volume is just, okay, well, these are probably simpler than these. So I'm just going to use this one. You could do it using this one, no problem. So these are going to be my limits of integration, if you like. Okay, these go with the y, so I'm going to put a dy there, and these go with the x. So all I've got to do, treat it like a regular integral that we saw yesterday, integrate the inside integral, and then integrate the outside integral. Okay, so I'm holding all the x's fixed, integrating with respect to y. So I replace y with x, y with 0 in the normal way. When I put in y equals 0, I'm not going to get anything, so I'm going to get something like this. So I'm going to get minus x squared minus a half x squared, which is, oh, hang on, yep, okay. So I'm going to get dx. So let me just keep going with this. So I'm going to integrate this. Yep. All right. So when I put in x equals 1, I'm going to get 3 on 2 minus a half, which is just 1. Phew. So what does this say? Well, it says the volume of the solid is 1 cubic unit. But that wasn't the hard thing. Although I made it look hard around here, this is what students find difficult because they're not used to describing two-dimensional regions. Okay? So my advice for you is to really concentrate. If you want to get good at these kind of problems, concentrate on how you describe in this case, the two-dimensional base. Okay? Now, you're also going to use this in 3 dimensions. So you're going to have to describe things mathematically in 3 dimensions later in this course, after I've finished my lecturing. Now, if you went through and used this setup for your integration, okay, so these would be the limits of integration, then you should get the same answer. So I'd encourage you to just verify that if you re-describe the region, both descriptions will give you the same volume. Okay. So here's another one. Mathematically describe the following region in two ways. So think of this as a base of some sort of solid. If we're going to, say, calculate the volume, we need to use double integrals. For that, we need to set up our double integral in the right way with the right limits of integration. Okay? So what I'm going to do, here's one that's been created earlier. In this one, I'm going to draw a vertical line. Where does that line enter the region? Well, it enters it at y equals x squared, and it leaves it at y equals 2x. So what I can say, sorry, that should be dots, that y is going to be greater than x squared, but less than 2x. And if I just move this vertical line from side to side, what's the interval that will sweep out all of the region? Well, just 0 to 2. So that's the bounds on my x. So who wants to have a go at part B? Who can do part B for me? What's the description going to be? Who thinks they can do it? Yes. So what's x going to be? Sorry, what's y going to be between? Correct. And we've drawn our horizontal line. That's it. Well done. Sorry. Now, it looks easy. Thank you, well done. But you'll be amazed at how many students they just can't do it. I think they underestimate it, and so they don't try. But without this kind of ability, you just can't do double integrals or triple integrals for that matter. So can you see how the domain, or the base in this case, is playing a huge role in the integration? It's not the integration that's hard. It's setting up the integral. It's describing the two-dimensional base of your solid, or the two-dimensional region that you're integrating over. That's the challenge. Okay, the integrals aren't that hard. You just do the inside one, do the outside one. Okay, this is a really good question. This is something that you might see on a class test or even in session. Sketch the region of integration R for this particular integral. Redescribe R, and hence, with that information, evaluate this double integral. Okay, so what we can do for this, we can take the region of integration just from these sort of limits. So x will be between y and 2, and y will be between 0 and 2. So let's just write that down first. So we were asked to sketch it and redescribe it. But let's just write it down first. Okay, so y is between 0 and 2, and x is between y and 2. So let's sketch the integration, the region of integration. Okay, so we want y between 0 and 2. So we're going to have two sort of constant and parallel lines. So one's the axis, the x-axis. we've got the line y equals x in there that will form some sort of boundary. Okay, and then they're going to sort of connect over here. Now, I guess you can look at that region and see two triangles. Which triangle is it? Is it the top one or the bottom one? Well, sorry, is it yeah, is it this one or is it this one? Which one is that region referred to? Is it the left one or the right one? Left? Right? Well, right. Let's go back to this. If I draw some sort of horizontal line, it's got to enter on this point, so that's right, and then leave it at this line. So it is actually this one. Okay? But hang on, I've sort of forgotten something here. Why don't I just, I've done what they've asked me to do. I've sketched the region of integration, right? Why don't I just integrate it? Why can't I just integrate that? What's the integral of sine of x squared, so sine of x squared, with an indefinite integral, antiderivative, with respect to x? If anyone can give me that in terms of an elementary function, I'll give you a HD right now. Okay, have I got any money? Oh yeah, $40. I'm an academic, so I don't get paid very much. But $40 if you give me the antiderivative of sine of x squared in terms of elementary functions. Going. Gone. Oh well, don't feel bad. There is no antiderivative in terms of elementary functions. So we cannot do that integral, that double integral, as it is. Okay? You can't do the inside integration in terms of elementary functions. You can do it in terms of, say, a series, but that's not an elementary function. So what we're going to do is switch these two and adjust the limits of integration. Now, let's say I switch the dy with the dx, can I integrate sine of x squared with respect to y? Yeah, you can. It'd be y sine of x squared. Okay? So the strategy here is to look at what you got. Okay, I can't do it. Let's see if I can flip or reverse the order of integration and see what happens. But I can't just flip those and flip those. I've got to redescribe my region. Okay, so I'm going to draw another picture of the same region here. And I'm going to use a vertical line. Okay, so let's redescribe. All right. This vertical line enters here and leaves here. So y is going to be between 0 and x. Okay, this is just the line y equals x or x equals y. And what's the interval for our x? If I just sort of move this either way, the line either way, I can cover the region just by going between 0 and 2. So they're the bounds on yx. So now what I can do is evaluate this integral by using these upper and lower limits of integration and just let's see what happens. So let's just let this be I. So it's going to be from 0 to 2 on the outside and from 0 to x on the inside. I'm still integrating the same function, and I'm swapping the differentials around. So let's do the inside integral first. Integrate sine of x squared with respect to y. Oh, that's just y sine of x squared. How good's that? Dx. Substitute in. Now, I've got a reasonably challenging integral to do. What would what's my antiderivative of x sine of x squared? Well, you could use a chain rule if you wanted to, or you just write it down, right? The sine's got to go to a cosine, and so the sine's got to go to a cosine, and then you think, okay, if I differentiate this, that's going to come, sorry, negative cosine. This is going to turn to a 2x, but I've already got an x out there, so what I can do is just multiply by -1/2 to adjust it. So just subbing in x equals 2 and x equals 0, I'll get something like this. Now, that's a reasonably challenging question because it asks you to do a lot of things. It asks you to not only sketch the region of integration, but redescribe it, switch the order of integration, and then actually do the integration. So that's a reasonably challenging question. Yes? So radians. Yep, that's a good question. Whenever we, in calculus, and we talk about cosine 2x or sine x or something, the variable is always in radians. Okay? I mean, to give you an idea of why that's true, let's just cover this up and talk about x sine of x squared. If x is 90 degrees, how do you multiply by 90 degrees? Doesn't make sense. Okay? All right. Now, some general properties of double integrals. They would be the kind of properties that you would expect from integrals. They're additive. If the function you're integrating is non-negative, then the double integral is going to be non-negative. Additivity is an interesting one. Probably 4's the most interesting one out of the lot. If you have a region, R, that's really complicated, and it's hard to describe that region in mathematical terms. What you can do is slice up the region into simple regions, R1 and R2, describe those, integrate them separately, and then add them together. Let me give you an example. Suppose I had, this is my region of integration. Okay, so the z-axis is coming out. Maybe there's a surface associated with that, and you want to calculate the volume. What I could do here is slice it up into two potentially simpler regions. Describe those mathematically, integrate over both of those regions, add the results together. Very last thing, and I did say this in the lecture yesterday, double integrals can be used to calculate area. Again, what you're doing, you're just covering some two-dimensional region with rectangles. Okay, you're adding up all those, the area, all those little rectangles, and you're taking the limit. So this is an important concept. So you can think, oh, okay, well, It's just the double integral of the constant function 1 over our region of integration. And I've provided an example. Now you might look at this. Okay, this is, when I say below down here, it's actually above, up here. Now, you might look at this curve. It says, okay, calculate the area in this blue region. You might think, well, I can do that with single integrals. Yes, you can. You can. But this example also gives you the, I guess, a relationship in this sort of context. Here's your double integral. If I do one of them, I actually get the single integral that I would have probably used to calculate the area at school. Okay? But don't ignore double integrals in area. Okay? You may be tested on it, and we may want you to use double integrals to calculate area.